In this video, I'll be talking about inertial frames of reference and Galilean transformation, which are, we can say, which are the backbone of classical mechanics, and also it forms a good basis for more complex topics in modern physics. So, before getting into inertial frames of reference, I think I need to explain what a frame of reference is. So, a frame of reference is just a system of coordinate axes which clearly specifies the position of a particle or an event in 2 or 3 dimensional space. The fundamental requirement for a reference frame is that it must be rigid. The simplest reference frame is a Cartesian system of coordinates, which we all are familiar with, in which the position of a particle or an event is exactly defined by its coordinates xy and z along the 3 perpendicular axes. There exists also a reference frame with the 4th coordinate time, which is perpendicular to the 3 spatial coordinate axes of x, y and z. Such a frame is called space-time frame. And since all rest and motion are relative, the position of rest or the state of motion of the same particle may appear to be different from different frames of reference. Let's consider examples. A ball dropped from the window of a running railway carriage appears to fall vertically to the person at the window, but to take a parabolic path to a person outside the train. And also another example, a point on the rim of a rotating wheel appears to us from our frame of reference on the earth to be taking a cycloidal path, but to a person situated at the center of the wheel, the point appears to be moving along a circular path. So we can say a object at rest or state of motion, it can be different. The state of an object can be different in different frames of reference. So let's analyze Newton's laws of motion. We all are familiar with laws of motion. The first law is a body must continue in its state of rest or uniform motion along a straight line unless acted upon by an external force. Second law, the rate of change of momentum is proportional to the impressed force and take place in the direction of force. And third law, to every action there is an equal and opposite reaction. So the first law gives us a definition of force as the causal agent of motion change. That is, for an object in state of motion, to change that state of motion, we need to apply force. So if there no force is applied, there won't be any change in velocity and therefore no acceleration. If F is equal to 0, A is equal to 0. And the second law gives us a measure of force as the rate of change of momentum. F is equal to dp by dt, and here the condition is we have to consider the mass as constant and also independent of velocity. So F is m into dv by dt, which is ma. Therefore again, if acceleration is equal to 0, there won't be any force, which is basically the first law. So we can say the first law is only a special case of the second law when force is equal to 0. And let's think about the limitations of the second law. Second law and first law. First law is again it is a special case of the second law. So let's check the limitations of the first 2 laws of motion. And yeah, the obvious limitation is that in the second law we have to consider mass as constant, which is not always the case. For example, a falling raindrop which increases in mass as it falls due to more water vapor condensing around it. And the second example is that a rocket hurtling into space ejecting burned up fuel and thus shedding more mass continuously. And another example, a body moving with a velocity which is an appreciable fraction of the velocity of light in free space. So that is, according to Newton's laws of motion, as long as we are applying force, we should be able to accelerate an object. But If a body attains the speed of light in vacuum, that is c, we won't be able to accelerate it any further, um, due to various reasons. And even if we apply more and more force, we won't be able to accelerate it. And there comes a concept of relativistic mass and some other concepts like that, so which contradicts Newton's laws of motion. And the third law too has its own limitation in that forces on two bodies interacting with each other are equal and opposite only if they be measured simultaneously, and it's impossible to do so. If, however, the time of interaction of the two bodies be sufficiently large compared with that taken by light to travel from one to the other, this condition of simultaneity may be said to be more or less satisfied for ordinary purpose. But this is simply out of question in the case of particles of atomic dimension, so the law ceases to hold good for them. Here, what he's saying is, let's say two objects, and the first object exert a force on the second one, and the second also exert a force on the first one. And we can say the moment the first object exerts a force on the second one, it exerts the same but the opposite force to the first simultaneously. But when we're talking about subatomic particles, or like small dimensions like that, or huge objects like planets, we can't say the force is experienced by the two objects simultaneously. So let's talk about subatomic particles like electrons and protons, and they mainly interact using electromagnetic force, which is mediated by photon. So let's say suddenly electron starts accelerating or interact with another particle, it won't be simultaneously felt or visible to the proton, since photon takes time to travel from one point to the other. The speed of photon is finite. So, and also let's consider two planets, which is one light year apart, and they both exert gravitational force on each other. So yeah, they both exert gravitational force on each other, and gravitational force is mediated by gravitational waves, which also has the velocity of light in free space. So if hypothetically, let's say one planet suddenly explodes or changed its path of revolution, or like changed its path, it won't be visible, or the other planet won't be affected by it for 1 year, because again the speed of light is finite. So the third law has also limitations, and the first two laws do not hold good in any and every reference frame. A body at rest in one reference frame may not appear to be so in another reference frame. Example, if a reference frame be rotating with respect to the first, the body appears to an observer in it to be moving in a circle. In fact, it is only in a very special frame of reference that the two laws hold good. Such a frame of reference is referred to as Newtonian or a Galilean, or usually an inertial frame of reference. The first law defines and the second law identifies an inertial frame of reference to be non-accelerating and hence also non-rotating. All other frames of reference moving with a constant velocity with respect to it are also referred to as inertial frames of reference. An inertial frame of reference being an unaccelerated one, the question arises as to whether it can be located on the Earth, which not only goes round the Sun but also spins about its own axis, and would thus impart a centripetal acceleration to a body in the reference frame based on it. Even the sun is not at rest but moving about the center of our galaxy, which is itself moving through space. So, the main condition for an inertial frame of reference is that it must be non accelerating. So, Earth has an acceleration which is very small, but technically we can consider Earth as an inertial frame of reference since it has acceleration. So, the nearby to being stationary or at rest and hence ideal for locating an inertial frame of reference are the fixed stars. So called because they seem to preserve their own arrangement or their relative distance from each other. This is not because we know them to be actually fixed in their positions, but because from the huge distance from them, here on the earth their velocity appears to be almost nil. It follows therefore that any rigid body situated in remote space far from attracting matter and fixed with respect to the fixed stars um, may be taken to be an inertial frame of reference, and naturally so also any other reference frame moving with constant velocity relative to it. However, for our ordinary purposes, the Earth serves well enough as an inertial frame of reference, and hence also the interior of a vehicle moving smoothly and with a constant velocity on its surface. And let's go into inertial importance of inertial frame of reference. So the first one is all our fundamental laws of physics have been formulated with respect to such a frame. So all our fundamental laws of physics like Newton's law and conservation laws. So all such laws are applicable on inertial frames of reference. And it is a basic assumption of the special theory of relativity that all fundamental physical laws can be so expressed as to assume the same form in all inertial frames of reference. So that is basically, let's consider two inertial frames of reference, which is a reference frame that is moving in a constant velocity with relative to each other. And if we let's say if we measure the distance between 2 points in both reference frame, uh, it has to be same. So yeah, that's what it is. We'll talk more about it later. And such a frame of reference is supposed to be isotropic. So that's all about inertial frames of reference. Inertial frame of reference and examples. So basically, non-inertial frame of reference is a reference frame that is accelerating, and we are taking different examples here. The first one is a reference frame with a linear acceleration. So let's say there are two reference frame. One is accelerating with the velocity a0, and the other is inertial reference frame. Let's say that is s, and the accelerating one, non-inertial one, is s dash. So a particle at rest in frame S will appear to have an acceleration minus a0 in frame S dash. So a particle having an acceleration a in the form of frame will appear to have an acceleration a dash is equal to a minus a0 in the latter. So that if m be the mass of the particle, force acting on the particle in frame S, F is equal to ma, and force acting on the particle in frame S dash, F dash is equal to ma dash. So we know a dash is a minus a0. So F dash is equal to m into a minus a0, which is ma minus ma0, which is F minus ma0. Then we are considering minus ma0 as f0. So we have the equation F dash is equal to F plus f0. And if force F is equal to 0, we have F dash is equal to f0. So that is, even if no force is acting on a particle in frame S, if force F0 is equal to minus ma0 seems to be acting on it from reference frame S dash. So the Newton's law of motion doesn't hold good in frame S dash, which again shows that it's a non-inertial frame. This this force F0 is equal to minus ma does not actually exist but appears to come into being purely in consequence of the acceleration a0 of frame s with respect to s, frame s dash with respect to s. So it is called fictitious or a pseudo force, and it is equal to mass of particle into acceleration of non-inertial frame with sign reverse. So here m into minus a0, which is minus ma0. Weightlessness in the elevator. If you consider an inertial frame, such as a reference frame of someone standing outside an elevator, the elevator and the person inside is accelerating downwards due to gravity at g. That is g. However, from this inertial frame of reference, there are no fictitious force because gravity is a real force. The person inside the falling elevator is being pulled downward by gravity, but there is no additional force acting on them in this reference frame. And but in the reference frame of someone inside the elevator, that is a non-inertial frame, we can say the elevator is in free fall. So it's an non-inertial reference frame because it is accelerating, and here the acceleration is acceleration due to gravity. And because of that, you need to introduce a fictitious force to account for the fact that the elevator is accelerating. From the perspective of someone inside the elevator, there is no physical force exerted by the floor to support them, and it feels as though gravity is not acting on them. This is because the fictitious force cancels out the gravitational force, making the person inside the elevator feel weightless. So here when we are looking at the equations, fictitious force acting on the particle f0 is equal to m into mass into acceleration of the particle in the acceleration of the frame in the negative sign. So m into here acceleration g, negative sign minus, so minus mg. The resultant force observed by an observer in the lift f1 in the lift f dash is equal to real force plus fictitious force, which is equal to f dash is equal to mg minus mg, which is 0. So the particle appears to be weightless in the lift. And another example of non-inertial frame is a circular motion. That is a reference frame in circular motion. Let's consider a frame of reference s dash be rotating about an inertial frame s with an angular velocity omega. It can be shown that even if no force be acting on a moving particle in the inertial frame, a fictitious force appears to be acting on it in the rotating from frame s dash, given by the pseudo force is f0 is equal to minus 2m omega v dash minus m omega square r, where v dash is the linear velocity of the particle as observed in frame s dash. And here we can see m omega square is the centrifugal force, and minus 2 m omega v dash is called Coriolis force. And here the fictitious force f0 is Coriolis force plus centrifugal force. So we can say centrifugal force is actually a fictitious force acting on a particle at rest with respect to a rotating frame. And since it keeps the particle at rest in the rotating frame, it is equal in magnitude but opposite in direction to the centripetal force acting on the particle on account of rotation of the frame. The Coriolis force 2 is a fictitious force that appears to act on the particle in the rotating frame when it is in linear motion with respect to the frame. As for example, a fly or an ant walking on a rotating piece of cardboard. Yeah, so this is all about inertial frames and non-inertial frames. As we have time limitation, I can't explain too much about a single topic, so let's go into Galilean transformation. Galilean transformation. So, if you observe an event from two different frames of reference, it will naturally have a set of coordinates in one different from that in the other. Equations relating the two sets of coordinates of the event in two frames of reference is called transformation equations, because they enable us to transform the observations made in one reference frame into those made in the other. If the two reference frame be inertial or Galilean ones, and if mass and time be assumed to be independent of any frame of reference in accordance with Newtonian mechanics, the transformation is referred to as Galilean transformation. And if a quantity is characterized by the same number in the two frames of reference, it is said to be invariant to the transformation. So let's consider some typical cases of Galilean transformation. So in this picture, there are two inertial frames of reference, S and S dash, and S is at rest and S dash is moving with a constant velocity v with respect to it in the positive direction of x, where v has to be very much less than the velocity of light in free space. Okay, then the two observers be stationed at the origins of the two frames O and O dash with their clock set to 0 when O and O dash coincide with or lie opposite each other, so that time is measured from the instant that the observers just cross each other. Let the position of an event at P as determined by the observer in frame S after time t be given by the coordinates x, y, z, and its position as determined by the observer in frame S dash be by the coordinates s, x dash, y dash, and z dash, and its time of occurrence by t and t dash as noted on their respective clocks. So clearly from this figure we can see S dash is moving relative to S with a constant velocity v in the positive direction. So the x coordinate of P, okay, there is an event happening here at P. That's what we marked as P. So the yeah, so the x coordinate of P in frame S will be greater than that in frame S dash by a distance Vt covered by S dash in time t, right? So here we can see the x coordinate of P in S will be greater than the x coordinate of P in S dash. Here I wrote S1, it is not S1, it is S dash. Yeah, so yeah, we can say H dash is equal to H minus Vt, and as there is no relative motion between the two frames of reference along the other axes of such as y, z, we have y dash is equal to v and y, and z dash is equal to z, and in Newtonian mechanics we consider time as absolute. So time is independent of any frame of reference, and we take t dash is equal to t. Thus the four transformation equations for the position of the event as observed in frame S dash are x dash is equal to x minus vt, y dash is equal to y, and z dash is equal to z, and t dash is equal to t. And the inverse transformation equations can be simply obtained by replacing v by minus v. Then we have x dash is equal to x is equal to x dash minus vt, so x dash plus vt, y is equal to y dash, z is equal to z dash, and t is equal to t dash. So since the position of the event is not same as
measured in the two frames of reference, we say that position is invariant to Galilean transform is not invariant to Galilean transformation. That is, the position in two reference frame, inertial reference frames are different. So we say it is not invariant to Galilean transformation. And now let's consider distance or length. For that, we are assuming two events occurring at 2 points P1 and P2 in both the inertial frames. In S1, two events are happening, and S2, two events are happening, and the distance between P1 and P2 be P1 and P2 be two events at S. Okay, so the distance between those two along the x-axis such that the coordinates in the stationary frame s dash are, it's not s dash, stationary frame s are x, y and z, and x2, y2 and z2, and in the moving frame s dash x1 dash, y1 dash and z1 dash, and x2 dash, y2 dash and z2 dash respectively. The distance between the two events is so x2 minus x1, which is equal to delta x. In the inertial frame x, not x, s, and x2 dash minus x1 dash is equal to delta x dash in the reference frame s dash. So the transformation equations for the event at p1, we know we have already made the transformation equations for position. So we are taking the transformation equation x1 dash is equal to x1 minus vt, and all the other coordinates are not changing, so we can say y1 dash is equal to y1 and z1 dash is equal to z1. So the transformation equations for p2 are like the same way we made the transformation equations for p1. So to find distance, we are taking x2 dash minus x1 dash, which is equal to delta x dash, which is x2 minus vt minus x1 minus vt, which is x2 minus x1, which is delta x. That is the distance between two events as measured in either frame of reference is the same irrespective of the values of v and t, provided the observations are made simultaneously in the two frames. So it can be easily seen that if delta x be the length L of a rod as measured in frame S with its endpoints at x and x2, and delta x dash its length L dash as measured in frame S1 with its endpoints at h1 dash and h2 dash, we have delta h dash is equal to L dash, which is equal to delta L, which is equal to L. So we can say the length of the rod is same as measured in either frame of reference. So basically it's just that if you are taking two inertial frames of reference, and if you measure the distance in between 2 points or like two events in both the inertial frames of reference, the distance will be same, but we have to measure make the make the observations simultaneously in both frames. Okay, so yeah, so we can say length of the rod or like length or a distance is invariant to Galilean transformation. That is, in both reference frames it will be, in both inertial frames of reference, uh, the length or distance will be same. And now let's check if velocity is invariant to Galilean transformation. The velocity of a particle moving along the axis of x as observed in the two frames of reference s and s dash is given by, we are just differentiating position. So we get velocity u is dx by dt and u dash is equal to dx dash by dt dash, and time is same.
and we have the transformation equation for position. So we are differentiating that and we get u dash is equal to u minus v. So u dash is equal to u minus v. Since the velocity in two inertial frames are different, we can't say velocity is invariant to Galilean transformation. And also the inverse transformation gives u is equal to u dash plus v. So yeah, velocity is not invariant to Galilean transformation. Yeah, and then either of the relations for u and u dash, it will be noted, is the same as obtained by the Newtonian law of composition of velocities and is referred to here as the Galilean law of addition of velocities. Then acceleration, we are differentiating velocity, and when we do that and replace the velocity equation with the Galilean transformation equation, we get a dash is equal to a, which is a dash is the acceleration in the moving inertial frame s dash, and a is the acceleration in the moving in the stationary inertial frame s. That is, acceleration of the particle is the same as measured in either frame of reference, and so we can say acceleration is invariant to Galilean transformation. Galilean invariance. We have already talked about Galilean invariance and we have checked acceleration, whether acceleration, velocity, or distance is variant to transformation, Galilean transformation or not. So the Newton himself had his own conception of relativity, is borne out by the statement in one of the corollaries to his laws of motion that the motion of bodies included in a given space are the same among themselves, whether that space is at rest or moves uniformly forward in a straight line. This means, in other words, that if we are drifting along at a uniform speed, as for example in a closed spaceship or even a smoothly running railway carriage, all the experiments performed and all the phenomena observed inside the ship or the carriage will appear to be the same as though the ship or the carriage were at rest, and we cannot therefore determine whether we are at rest or in uniform motion. This is actually an interesting topic. Like, this forces us to think out of the box. Like, we can say in a way the reality is relative. Like, we can't actually be sure if we are at rest or in motion, because it will be relative to the reference frame. And this is the concept of Newtonian or classical relativity, and clearly implies that the fundamental laws of physics are identical in all inertial or Galilean frame of reference. That is, they are invariant to Galilean transformation, and hence the term Galilean invariance applied to them. So, checking if the fundamental laws are really characterized by Galilean invariance. So, the fundamental laws like Newton's laws and conservation laws. I don't know if I have the time to explain all these because of the time limit. So basically, Newton's laws of motion is invariant to Galilean transformation. Since okay, let's consider two a reference frame S and S dash. Both are inertial frames, and two forces F and F dash is acting on both the frames. So when we calculate the force, we will find that both the forces are same. So we can say force acting on the particle is the same in either frame of reference, or that the Newton's law of motion is invariant to Galilean transformation. And the second is law of conservation of momentum, and here also we can say law of conservation of momentum is invariant to Galilean transformation, but the momentum of the individual particle is not same in both reference frames, both inertial reference frames. So the moment of the individual particles is not invariant to Galilean transformation. And the third law is law of conservation of energy. So energies of the individual particles are different in the two frames of reference. Their total energy remains the same. Like we said about momentum, energies also, the energies of the individual particles are different in both inertial frames, but the total energy of the system remains constant. So we can say it is also, I mean, remains constant means it will be same. So we can say it is invariant to Galilean transformation. Although all these fundamental laws of physics are thus found to be invariant to Galilean transformation, that is to be the same in all inertial frames of reference, this is so under the severe limitation of mass and time being arbitrarily assumed to be invariant in all frames of reference. That is, mass and time is um, assumed to be constant or like independent of inertial or reference frames, there being really hardly any justification for it. We see in Einstein's theory of relativity, they do change with velocity, though the change manifests itself to any appreciable extent only at very high velocities, comparable with that of light in free space, that is c, the constancy of which alone in all frames of reference, it may be pointed out, forms a basic postulate of Einstein's theory. Our fundamental laws of physics are therefore invariant, strictly not to Galilean, but to what is called Lorentz transformation. At velocities very much lower than c, however, all Lorentz transformations do get reduced to Galilean ones. Okay. So here, even though all these fundamental laws of physics are invariant to Galilean transformations, when particles move at very high speed, that is like light, we can't say it is. It can be applicable in Galilean transformation. So there we have to use Lorentz transformation, and yeah, we will talk more about it later. And non-inertial frames of reference and fictitious force, we have already talked about that. And limitations of Galilean transformations. So like we said earlier, the equation for a spherical electromagnetic wave in system S with the speed of light c being constant is x1 square plus x2 square plus x3 square minus c square t square is equal to 0. So for this equation to remain invariant in a second frame S dash, we would expect it to look the same. However, when Galilean transformations are applied, it becomes clear that the form of the wave equation doesn't remain the same. So this shows that Galilean transformations cannot preserve the form of electromagnetic wave equation. This failure suggests that a different set of transformation, which later become known as Lorentz transformation, is necessary to correctly describe electromagnetism. So that is the limitation of Galilean transformation. It can be applied to electromagnetism. So later, Lorentz transformation were introduced, like that that is applicable to almost all the laws of physics. And in Galilean transformation, if light speed c was subject to Galilean transformation, it would vary depending on the observer's motion, which contradicts experimental observations like Michelson-Morley experiment, showing that the speed of light remains constant in all inertial frames. So yeah, in Newtonian mechanics and Galilean transformation, light is not considered as a, the speed of light is not considered as a constant. The speed c was yeah, it is not considered as a constant. Um, the speed of light were, it is believed that the speed of light will be different in different frame of reference or inertial frames, so which contradicts the experimental observations like Michelson-Morley experiment, which showed that the speed of light remains actually constant in all inertial frames.
Generalized, it generalized Galilean invariance, that is electromagnetism. The laws governing electromagnetism were not invariant to Galilean transformation. So, the first postulate of special theory of relativity is that um, all laws of all fundamental laws of physics has to be must be same in all inertial frames. So that is, there is no absolute frame of reference in the universe, and the laws of nature apply equally regardless of one's constant velocity. Thus the behavior of light and other phenomena must remain consistent across different inertial frames. And the second postulate is consistency of light speed. It's not consistency, it's constancy. Unlike sound or other waves that depend on a medium, light propagates through vacuum with a constant velocity of speed c, independent of the motion of the source or observer. This postulate challenges the classical view, which assumes speeds add up and suggests that time and space must adjust to maintain this constancy. Right? So, this requirement led to the groundbreaking idea that time and space are interconnected, with time dilation and length contraction arising as natural consequences. We can, in a way say that the second postulate kind of changed our understanding about the universe, because until that time, light was considered as uh, not constant, right? So, and time and space as something constant uh, which can't be changed. So, Einstein, in his special theory of relativity, said that the speed of light has to be constant in all inertial frames of reference, so that in order to make up for this speed velocity of light, time and space have to adjust to maintain this constancy. So this led to an idea that time and space are actually interconnected, and there are some interesting phenomena like time dilation and length contraction arising as the consequence of this. And yeah, transition to Lorentz transformations. To account for the constancy of the speed of light and the invariance of the electromagnetic wave equation, Lorentz transformation replaced Galilean transformation. Lorentz transformation suggests both space and time coordinates between frames in a way that preserves the speed of light and accommodates the effects of high velocities, making them essential for accurately describing phenomena at relativistic speeds. So, after Einstein's special theory of relativity, it became essential that there should be equations that are applicable to electromagnetism as well. So, Lorentz transformations replaced Galilean transformation, making them Lorentz transformations. In Lorentz transformation equations, both space and times are adjusted so that the speed of light can be considered or can be taken as a constant. So Lorentz transformations can be um, used for objects with the speed of light as well. So yeah, it making them essential for accurately describing phenomena at relativistic speeds. And yeah, so we talked about frame of reference and inertial frames of reference, non-inertial frames of reference, and Galilean transformation, Galilean invariance, and transformation equations, um, and classical relativity, limitations of Galilean transformation, Lorentz transformation, Einstein's special theory of relativity and its postulates. So the last topic is application of inertial frames and Galilean transformation. So in classical mechanics, the velocity of objects are very much less than the speed of light. So we can't use Lorentz transformations there. We have to use Galilean transformation. So we can say uh, Galilean transformations are foundational in classical mechanics. And relative motion analysis, understanding relative motion between different frames, just such as between a moving car and the ground. For that, we need to understand what a inertial frame or a reference frame is, and Galilean transformation help us to transform the equations of an object in one inertial frame to another. Yeah, and limitations for relativity. In modern physics, the limitations of Galilean transformation highlight the need for Einstein's theory of relativity at high speed. Like we said earlier, for electromagnetism, Galilean transformations are not applicable. So, uh, it highlighted the need for Einstein's theory of special theory of relativity and Lorentz transformation, which is applicable on electromagnetism and objects with high speed as well. So that's it. These are the topics I prepared for. I hope you could understand what inertial frames of reference and Galilean transformation is. This is an interesting topic, and I really hope I didn't make it boring. So, yeah, thank you.